lab. They'll say, "Ah, that's a good news," because they don't want to do labs. So this particular topic is very easy, but for some reason, students find it difficult. There are two topics in CCNA that students don't like. Let me show you the two topics. What's going on here? Just a minute, guys. Just a minute. Okay. When somebody told me to, I think, maximize this, I think it has affected my screen. Yeah. Just a minute. Let me solve this problem. I think I over maximize this screen, so it's messing up. Okay. I think I know what to do. Okay. I think I'm good. So please, I hope you can still see my screen. There are two topics the students don't like in CCNA. They have challenges two topics. One is subnetting, and the other one is spanning tree. We have conquered this one. We're about to conquer this one. STP, spanning tree protocol. So I don't know why. In fact, some people they find subnetting easier compared to spanning tree. For me, spanning tree is even easier than subnetting. But for some reason, students don't like spanning tree. So I've decided to approach this in a different way. All these years I've been teaching this. If you watch my other video, you see that the way I'm teaching this in today, I'm teaching today's class is a bit different from the way I taught it before. Because as a trainer, you always crack your brain on how can I communicate this? How can my student? How can I carry this message along? Because until I'm able to reproduce myself in you guys, my job is not done. Until I am able to reproduce the knowing this thing the way, I mean, for you people knowing this in the way I know it, my job is not done. That is the way I feel as a trainer. So just follow me carefully. So the topic we want to take care of is spanning tree, and I'm going to just give you a background. Spanning tree protocol. Spanning tree protocol. So it's just long story with some demonstration. Spanning tree protocol. So what is this spanning tree protocol all about? Now, if you recall, I've said something in this class before. I say every technology you are learning is solving a particular problem. Any technology you are learning in this IT field, it is to solve a problem or prevent the problem. So whenever you are learning a particular technology, what should be at the back of your mind is what is this? What problem is this technology solving for us? And how you can apply that knowledge. Because it's not good enough for you to know how to activate or implement a technology. You got to know the application of that technology. So I need you guys to follow me carefully. And this is one of the technologies that people hardly use in the field. People hardly use this, and I'll tell you why. So what is this spanning tree protocol all about? This spanning tree protocol is all about layer 2 redundancy. Layer 2 redundancy. When you hear redundancy in networking, does not mean something that is useless. Redundancy in networking simply means backup. Backup. So spanning tree protocol is creating a layer 2 backup for us. How? Do we really need it? You are the one to decide. For some big organization, they don't have a choice. They need to use spanning tree to achieve layer 2 redundancy. So what do I mean by this layer 2 redundancy? Let me give you an example. Let's assume you have a switch. This is a switch now. There are, let's say, a few people connected on this switch. And then you have exhausted all the port on this switch. Definitely you will need to connect, you will need another switch in order for you to extend that network. Then people will be connected to that switch as well. So let's call this one switch A. Let's call this one switch B. So people from switch A that are plugged on switch A will be talking to people on switch B. And people on switch A will be talking to people on switch B, passing through this connection here. So what if something happens to this cable here? If something happens to that connection, that means people on switch A are now isolated. They cannot talk to people on switch B because there is no backup. There's no backup. So the job of spanning tree, or let me say what we want to achieve in today's class is we cannot afford to use one cable. We want to have two different connections. Why? If one goes down, the other one is working. But how are we going to achieve this? Because if there is no protocol in place to help us manage those two connections in such a way that the two of them will not be open simultaneously, and if one goes down, the other one is open automatically. If that one that goes down comes back, that one that is probably working can go back to as a backup. We need something to manage those connections, and that is the job of this protocol. So do you only talk about spanning tree when you are talking about layer 2 redundancy, meaning layer 2 backup? If I like between this connection, I can use 3 different connections. I can use 4, I can use 5, I can use 6. It all depends on the design or the policy of the organization. But the best is just to have 2 connections now. So why do we need 2 connections? If one link goes down, the other one will come up automatically without us having to do anything about it. And that is the job of spanning tree protocol. It manages this link and makes it like somebody watching over the links and make sure that it is only one link that is happening, that is working at any point in time. So the question now is, can't we have the two links working simultaneously? For now, no. In our next class, yes. Because if you make the two link, or let me put it this way. If for any reason right now, I went and disabled spanning tree and decided to connect 2 cables together, we're going to run into trouble on this our network. There will be few problems. Number one, there will be loop. There will be what is called a switching loop. I'm going to explain that. There will be MAC address instability. MAC address instability. And then you're also going to have broadcast storm. What do you mean? So Roland, if spanning tree is disabled, because I can disable spanning tree on the tree, on the switch rather. If spanning tree is disabled and we decided to connect 2 different cables, these are some of the problems we are going to run into in the network. Yes, I'm recording. These are some of the problems you are going to run into on the network. I'm going to tell you guys something. I hope somebody will not go and try it somewhere. So what is a switching loop? Let's say this is Roland. He's trying to send a message to Pedro on the other switch. The message will go through, let's call this one link A, LA. Let's call this one link B, LB. The message, this switch A will forward the message through link A and forward the same message through link B. When the message gets to the other side, it will come in through the first link. Then the switch B will deliver the message, let's say from the first link, whichever one gets there first. Then that same message gets to the switch again through link, the second link. The switch take a look at this, the message and say, you know what, I've delivered the message before. Send it back to the other switch. This switch will send it back and say, no, the guy that is supposed to have this message is on you. No, it's not. I've delivered the message. No, it's not with you. It's on you. It's not with me. It's not on you. It's not with me. That is called a switching loop. The message just keep on traveling on the network forever. That is going to consume your bandwidth. You are going to have to break this in manually by just unplugging the switch of the cable. So if the 2 links are happening simultaneously because our spanning tree is not working, or we have disabled spanning tree, we are going to have a loop. Another problem, if the two links are working simultaneously, see another problem you're going to have again. Let me show you another problem you're going to have again. If the two switches are working, two links are on simultaneously here now. So let's say this is the first link, this is the second link. Pedro is plugged on port F0/10 on the other switch. And I am connected, this switch is connected on, let's say, F0/20. And then the other port, let's say F0/21. This switch will tell switch A, you can reach Pedro through port 21. You can reach Pedro through port 20 and 21. So on the other side, the guy will put in his MAC address table. If I need to send a message to Pedro, Pedro is available on port 21. In that same MAC address table, Pedro is available on port 20. Then it will be now be switching. No. I can't have this Pedro with two different ports now. Pedro is on port 1, on port 20. Pedro is on port 21. Pedro is on port 20. It just be the MAC address will become unstable because the two links are open simultaneously. That's one of the problems when spanning tree is not working. And then the last one is broadcast storm. If there's any broadcast, you guys I've talked to you guys about address resolution, bro. That one is crazy. If there's any broadcast from anybody here, it goes through link 1, it goes through link 2, it just be moving on the network here and there. So guys, you cannot afford to disable spanning tree. And the good news is spanning tree is active by default on your switch. But take notes and mark my words, guys. Spanning tree is active by default on managed switches. Managed switches. Meaning the switches that are configurable, managed switches, not plug and play. I have talked about plug and play switches before. Those are the switches that you cannot configure. The way you bought it from manufacturer is the way you will use it. Just connect computers to them. You can't do anything on those switches. You can't configure security. You can't do anything. So if you decided to use plug and play switches and you want to practice what I'm teaching you right now, you are going to bring down your network. Everything will just get choked. Switching loop, MAC address instability, broadcast storm, everywhere we just lock down. Let me give you another scenario. So these are the problems that spanning tree came to solve for us. Spanning tree will make sure that when you have two different links, the two of them are not open simultaneously. One is open, the other one is shut down without you doing anything. Spanning tree will make sure that there is no switching loop. Spanning tree will make sure there is no MAC address instability. Spanning tree will make sure that it gets again broadcast storm as a result of two different links open simultaneously. And then we will be able to achieve that redundancy. So one link is up, the other one is down. When that one goes down, the other one comes up. I'm going to show you guys right now on my packet tracer. Without me configuring anything, we have not even started any configuration. Spanning tree will do its work. But before then, let me show you guys something. Please don't try this, because that can bring down your network. If you go to your organization, wherever you work, there are some ports on the wall where you used to plug your computer. Most people have faceplates, even though wireless is now becoming very popular. That port on the wall, of course, there's a cable from that port that goes to the switch. And if you now have two ports side by side, if you plug your network cable on this port here and bring it to the other port here, so it's more or less like you're on a switch. You plug on one port and you bring the cable to the other side. Just like you are trying to, if you have an extension, you plug one wire on two different ports. If this switch does not have STP, if it has STP, it will shut down one of the ports. If it is a plug and play switch, you know what it's going to do? That network is going to come down. It doesn't matter how big that network is, as long as there are connection of switches, no segmentation in between, it's going to come down. Why? Because there will be a loop, and that loop it will cause broadcast storm. There will be massive storm on the network because the switch you are working with is plug and play. And there is no guard against that loop. So don't practice this, please. I just have to tell you that because you are being trained as professional. So now, let me show you guys something. I'll launch my packet tracer and bring out two switches. Now, ideally, you guys know that we only need one cable to link two switches together. So I'm going to link these two switches together. Ideally, that's all we needed. But based on our discussion, we want to create room for backup, meaning we are looking for a situation whereby if one link goes down, the other one comes up. So I'm going to use two different cables. Now you will see what is going to happen right now. So I'm going to carry another cable and plug between, let's say, port 2, 0/2, and 0/2 on the other side. You will see the way spanning tree will treat this link right now. This connection, and I've not done anything. I mean, I've not done any configuration. So one link is open already. Let's see what happens to the second link. So take note of what happened on the second link. Take note of what happened. One link, the first link was open completely at both ends. This place turned green, this place turned green. On the second link, one side turned green, it blocked the other side. Of course, it simply means that link is not available. This is planetary at work. I've not done anything. Now let's now yank off that link that is working. That is working. Now let me remove the cable of that one that is completely active. Let me yank off that cable. Watch out what is going to happen. I yank off this cable. Now when I yank off the cable, it simply means something like the cable has gone bad or the port on one of the switches has gone bad. So if anything should happen to that link, you will see what Spanitry will do right now. And mind you, I have not done any configuration. Spanitry will do its job. And I've not done any configuration. So you watch out. Now this is slow. Before the end of the class today, we can make sure we can increase you can move to a different Spanish. You can see this now. The link is as open. I didn't do any configuration. That is Spanish doing its work. So when you have more than one connection between two switches, it blocks one link because you can only have one active link so that we don't run into trouble. Then when that one active line goes down, it opens the other one. That is how Spanish works. Let me now confirm to you that this thing is active by default on this switch. I'll go to our command line and just say show spanning tree. You see something here? Spanning tree enable. Enable protocol IEEE. We're going to talk about most of the things under this as we proceed in this. Guess what? I have not done any configuration. So the spanning tree is on. So what we want to discuss in today's class is the operation of spanning tree. Okay, this thing that he blocked one link and opened the other one. How did he make that decision? What if I have more than one switch or two switches rather? What if I have more than two connections? All of those things. The way you should know spanning tree, you should know spanning tree in such a way like before spanning tree will finish making his decision, you already know what spanning tree will arrive at. And you should be able to influence that decision if there's a need to do that. These are all the things we want to discuss into this class. So let's the journey start. So I just gave you background. So some most of the things at the beginning I will be skipping them because I've just explained them in my own way. So when we get to where we need to really pay attention to, I'll be talking on those. So spanning tree concept. So what is the big deal about spanning tree? I've just told you. It's just to help us to achieve layer 2 redundancy. Purpose of spanning tree. So I've talked about all of those in my own way because we want to achieve backup. We want to have a redundant network so that we'll have additional physical part, even though logically there is only one part that will be working at every point in time. I've explained that one to you. So even though you see two switches like this, and there are two different connections, there are two different physical connections, but the truth of the matter is one will be done, only one is working. That is the job of spanning tree. So it's a loop. So spanning tree will help us to prevent loop. I've talked about that. Loop, MAC address instability, and broadcast storm, and all of that. So look at their own topology now. They have a continuous connection. What do I mean by that? There are three switches, switch 1, switch 2, switch 3. Ideally, we don't need all-round connection. We just need one. What I mean by one is, okay, let's say I have 3 switches now. I have 3 switches. There is a computer here, there's a PC4, and there are, oh no, let me follow their own. Let me do it the way they did their own. So let's say there are two switches up here, then one switch down. So they name this one switch 3, they name on this one switch 1, and then they name this one switch 2. So if I have a computer here, PC4, and then there are some computer here on this phone. So ideally, all I need is just a connection maybe from this S3 to S1, and then here. People here can pass through S1 to talk to somebody here. Even if there are people on this computer here, they can pass through S1 to go and talk to people here. Why do I need this other connection here? For backup. Because if anything happens to these parts, people can still pass through this part. That is the essence. So you can see what they did here. They have a connection already. So if PC4 you want to talk to somebody in PC1 or PC2 or PC3, PC4 can decide to pass through this route or pass this display straight. So if any of the link goes down, PC4 is still having access. If the other one goes down, PC4 is still having access. So in essence, this is just a backup connection. So the reason for this is we want to try to compensate for failure. So when one link goes down, the other one comes up. That is the job of spanning tree. And of course, I've talked about the problem. Whenever you have redundant link, there will be fire on the mountain. You're going to run into trouble of broadcast storm. You're going to run into trouble of switching loop. You're going to run into trouble of MAC address instability. The link will just be unstable. There will be problem here and there. So if you don't have your spanning tree, those are all the problems you're going to run into. So I have summarized all of those ones. So the same thing here, you can go to have a loop. You're going to have a broadcast storm. I've explained broadcast storm. And then those are the problems you're going to have. And this is where the journey begins. We now want to study this spanning tree. This spanning tree I'm making noise about now. Let's study it deeply. Let's go deeper. So how does it do its work? This spanning tree, let's understand it. It uses an algorithm. Who designed this spanning tree? Let's find out. So follow me carefully now. Spanning tree algorithms. Spanning tree is based on an algorithm invented by Bradia Palmer. That's the person that invented spanning tree while working for Digital Equipment Corporation and published in 1985. So what is the job of this algorithm? When you hear algorithm, what happens? What comes to your mind? It's just a way of getting things done using some formulas or follow some policies. So the algorithm, that's the way they put the algorithm. Algorithm for distributed computation of a spanning tree in an extended line. Okay, so what is and I think this is one of the reasons why people don't like the topic or why it's confusing. I think it's a woman that designed the algorithm. Apologies, women in the house. I'm married to one of you, so people sometimes women can be difficult. Somebody said the reason why programming language is difficult because a woman started programming language. So that's the joke anyway. So before some people say they will not enter my class again. So our spanning tree algorithm, what else? Create a loop-free topology. How? By selecting a single root brain. I'm going to come and explain this. This algorithm stated that when you have two connections, one has to be blocked automatically. If not, we're going to run into trouble. And we can achieve a backup with that. So, okay, how now? Where all other switches determine a single least cost path. I'm going to come and demystify all of this one. Just follow me carefully. So this spanning tree, of course, we have said that it prevents loops from occurring. That's tautology here. By configuring a loop-free file through the network using strategically placed blocks. Okay. So let's just go ahead and see. How does this algorithm work? How? Watch out, guys. The first thing this algorithm does on the network is they select a root bridge. or a root switch. I don't know why they call it bridge. What do you mean by that? When you have two switches connected together, before spanning tree will start doing its work and making decisions, the first thing is they need to select root bridge. Who is the root bridge? That is the president of the switch network. If you had one more switch in call, maybe two different connections, they will still carry out election. And select which going to become the president. That is the first thing first. That is the first thing that spanning tree will do. So when you select the root bridge, what do you now do with the root bridge? All the people that lost the election need to now find a way to reach the root bridge. Meaning what? You will now think, if this guy is the root bridge, for instance, and this, let's call this one switch B, and this one switch C. Switch B want to go to the root bridge. There are two paths. I can follow the left, I can follow the right. So switch B will now find the best path to the root bridge. The best path to the root bridge. How? Based on the speed. The fastest one to the root bridge. And that speed is based on cost. I'm coming there. Just follow me. So the first thing is they select the root bridge. If there are 4 switches connected together on the network, and you have this kind of all-round connection, even if you don't have that, they will select the root bridge. Like this topology that I have on the screen right now, they have already selected root bridge between themselves. They've chosen the president. Between 2 or more switches that are connected together, spanning tree will get to work, and then they will begin to do election and select the root bridge. And every other person will now say, find their way to the root bridge. Why do they do that? We're coming to that. Just follow me carefully. So when you find a way to the root bridge, I've not finished what I wanted to say. Let's say you have decided that, oh, the best way to read root bridge is the right. What happens to the second link? You block it. If switch C has decided that the best way to read root bridge is through this left, what happens to the second link? He blocks it. All the way leads to the president first, and all the parts that are not being used must be blocked. That is the way spanning tree works. We carry out election. We select the president. Everybody find the fastest route to the president and block the second link. If that route that you're using goes down, then you can use the other part. That's the way they do this thing. I'm going somewhere. Follow me carefully, and we're going to demonstrate everything to you guys. So you select the root bridge, and you find like this. This bridge or this switch is a reference point for the entire network to build a spanning tree around. So when we have the root bridge, it becomes a reference point where everybody will now say, okay, all the way leads to this guy. Because as a switch, you have 2 different links. You need to block one of the links. How will you know the one to block? You must choose a part of the root bridge, and that becomes the active part you'll be using. All the switches on the network that have more than one link to the root bridge must block one of the links after they have made up their mind on which one to be using to go to the root bridge, which is the reference point for the entire network. So after that, what happens? You block redundant part when you have found the primary route. And this will create a loop-free topology. And what happens in case of failure? You are going to recalculate. I remember that I have 2 links now. I cannot be stranded here. I have 2 cars. One is done. I carry the second car. That is the basic operation of spanning tree algorithm. But I like the way they put it more in this under this STP operation. It's a form of tautology, but I prefer this part. Watch out, guys. STP operation is still under the algorithm, because the algorithm creates, under the algorithm you have operation going on. Look at what they said here. The same thing, but in a different way. So look at what they say. Using the where's my pen? Okay. Using the spanning tree algorithm, STA, STP builds a loop-free topology. Watch out. In a 4-step process. Only if you like have 100 switches, 200 switches, 1 million switches connected together, this is what you are going to get. First thing first, they elect the root bridge. I just explained that now. Who is the root bridge? The president of the switch network. So If you need to jot this part down, you jot it down. Because I'm going to now go and explain and draw. After electing the root bridge, what happened? They elect the root ports. So what is the root port, guys? Let me show you something here. Let's assume we have, let me make it for switches. Watch out, I need your attention now. Let's call this one switch A. And this guy has won the election, is the root. Let's call this one switch B. Let's call this one switch C. Let's call this one switch G. So now, this guy won the election. That is switch A. So so switch B needs to make up his mind on where to pass through to go to the switch A, to the root bridge. Switch C needs to make up his mind on how to go to the root bridge. Switch D also needs to make up his mind on how to go to the root bridge. So let's work with switch C. Let's assume, based on calculation, switch C, let's call this port F0/1 and the other port F0/2. Switch C has decided that the best path to reach the root bridge is this route, not the other side. So you know what switch C will do to the other port? It will shut down the other port. And you know what? These ports that the switch C, please take note now, because this got me for a long time. Until when I went to South Africa for my CCNP, that was when I understood this part very well. You know, I always confess my sin in this class, or anytime I'm teaching. This port that this switch is using to go to the root bridge is called root ports. Yes, I'm down to heart in my class. The port that the switch is using, that active port on that switch, is called a root port. So if switch D right now has decided that this is the best part this port is what it will be using to go to the root bridge, and this is the best part, the port that is using actively now is the root port. Because I used to think the root ports are on the root bridge, guys. The root ports are not on the root bridge. All the ports on the root bridge are called designated ports. All the ports on the root bridge are called designated ports. All of them. But the ports that the switch is using to go to the root bridge at that point in time is called root port. And the other port that is blocked at this point in time is called block port or alternate port, because that one also can be used later. So you need to know all of these ports: root port, designated port, alternate ports. So if I did not win the election, and I have decided that the best way to go to the root bridge is through the route, I'm going to show you why they make that decision and how they make that decision. That port you are using to push message out to go to the root bridge is called the root port. The other one you block is called alternate port. What happened to all other ports on the computer? Because computers will be connected to this switch, all those ports are called designated ports. So in this class, you must be able to differentiate between root ports, designated ports, and alternate ports. Root ports, designated ports, and alternate ports. You should be able to explain it to anybody, because this will help you in this particular topic. So don't ever mix it up like me. Root ports are not on the root bridge. All the ports on the root bridge are called designated ports. And the ports that are on the switch that is being used to go to the root bridge, the one that is actively in use is called root port. The one that is blocked is called alternate port or block port. This is how all the switches will make decisions, so they know the links to block. And you will find out how the switch won this election. And you will see how we can rig this election, because we may not be satisfied with the switch that won the election. Because sometimes the old switch on your network, the oldest switch will win the election, and it may not be the most powerful switch on your network. And you don't want the weak switch to be the reference point for your network. So we will go to rig the election. And the most funniest thing about this particular topic, all the commands that we issue, they are not more than maximum 4 commands, and we're done with the class. But the concept back, talk plenty. You have to talk. So take note of this. I'm going to move on now. Take note of this. Now, I'm going somewhere. So at least I've communicated some concept. They must first of all select who becomes the root bridge. Then all the way leads to the root bridge. By that, they select the root port, designated port, alternate port. But I need you to also understand some things here, guys. During STA and STP function, switches, I said those switches will be talking. How are they talking? What is in their love letter? Bridge Protocol Data Units. They use BPDU. Switches use BPDU to share information about themselves and their connections. So once you drop switches like this on your network and they are all connected together, they begin to gist. They begin to gist between themselves. You think it's only humans that gist? Even devices talk to themselves. And in the discussion, they will now realize, okay, based on this, you know what? We are going to select you as the president of this network. So the BPDUs are used to elect the root bridge, the root port, designated port, and alternate port. So what is in that BPDU? We're going to see all the information in the BPDU. Because when I want to gist with you right now, the gist is going to be all about maybe what I ate, where I've been to today, where I'm coming from, and all of those things. It's just more or less like, tell me about yourself. Switch A, you're welcome to this discussion. Tell us about yourself. So watch out. What is in the BPD? One of the things they actually, for now, each BPDU contains bridge ID, which is also bit. Each BPDU contains bridge ID. So what is a bit? That's identify which switch sent the BPDU. This is like the identity of the switch that sends the love letter or the gist. And this bit is involved in making many of the spanning tree algorithm decisions, including the root bridge and the port row. So this bit, this bridge ID, what is in that bridge? Or how did they achieve this bridge? Watch out. The bit, guys, watch out. The bit contains a priority value of that switch, the MAC address of that switch, and extended system ID. The bit. So the combination of all these three makes bridge ID. And the lowest bit value, guys, this is key. The lowest bit value is determined by the combination of these three fields. Where am I going to? I'm going somewhere. I said they will always carry out election. And somebody is going to win that election. Guess what? The person that will always win this election is the person with the lowest bit. So how do you identify the lowest bit? We said the person that has the lowest bit, that is the lowest bridge ID, which is a combination of priority value, MAC address, and extended system ID. We win the election. Is this fair? How? Let's find out. So these are the three things that makes up a bit. The bridge priority, guys. The bridge has a priority number. The default priority value for all Cisco switches is 32,768. So that means the bridge priority, the priority number is a tie, is the same on all the switches. 32768. All the Cisco switches you are going to see, they are going to have this priority number. Extended system ID. This point to the VLANs that you have. And by default, most of the time, they are also the same. So extended system ID, also a tie. But there is something that will never be the same on your switches. MAC address will never be the same. So it therefore means when you have two switches connected together and we need to carry out election, since the bridge priority is the same, the extended system ID is the same, any switch with the lowest MAC address will automatically win the election. Now your knowledge of your hexadecimal comes in again now. Let's find out from those two switches that brought up. Let's find out who won the election and how the person won the election. Once you understand this, we're good to go. Let's find out, guys. So two switches. I brought two switches out. So let me name them so that we can differentiate between the two of them. Let's name this one switch A. SWA. So guys, one of these two switches is a root bridge. One of these two switches won the election. So who won the election now? Let's find out. Uh-oh. Sorry guys. Who won the election now? Let's find out. Back to that command I issued earlier. Show spanning tree. Show spanning tree. I will hit enter. This guy will tell me something here. Spanning tree is enabled. I've talked about this briefly before. He's telling me about the root ID. That means you are not the root. You didn't win the election. Because every other switches must point us to the root. So it's telling me that the root priority is 32768. This is the MAC address of the root. And this is the costs to get to the root. We're going to talk about all of this. These are the ports. Okay. That means you didn't win the election. Let's go to the second switch and see something. Show spanning tree. Look at this guy. I am the king of this network. Now me be the king of this network. Really? So switch B won the election. How did switch B win this election? So when you get to a switch and it's telling you he's the king, you know he's the king. He won the election. And how will you confirm that he's the king? Okay, if you look at the priority up and the bridge ID is the same thing. I'm the one that won this election. If you look at the MAC address of that switch and the address on that bridge ID, you know that you're actually talking about the same guy. He's telling, I say that me, I won this election. How did you win the election? Let's now compare the two MAC addresses of switch A and switch B, which I can find on switch A. We know that the priority will be the same. And somebody will be telling me, how come the priority is 32769? Here I said it's 32768. Guys, the VLAN number will be added. That is the system extended system ID will be added. That's why you are saying 3276, because we are just on VLAN 1. We didn't create any VLAN, and this will be the same all over. So let's now go to that switch A and compare their MAC addresses, because we can see the two. This switch A, where I am right now, this is his owner identity, his priority number, his MAC address, some other information that I have not talked about. So if you look at this MAC address now and compare it to this MAC address, you see that one of the two MAC addresses, one is lower than the other. Let's find out. Let me write it out. The switch, this is the MAC address of this switch where we are right now. 0050.0FF, oh sorry, this is E21C48. Then the one that won the election, this is the guy that won the election. 00400B060A1. Now, if you are beginning to compare their numbers, 00 is the same. 00 is the same. Between 4 and 5, which one is lower? You see that this 4 is lower than this one again. So I don't even need to continue again. This MAC address is lower. That's how the guy won the election. The guy's MAC address is lower than the one up here. That's why switch B won the election. So in a sense, what the switch use now, if we have not tampered with anything to make decision, is MAC address. So if you have 4 switches connected together, they all will discuss between themselves. Whoever has the lowest MAC address is going to win that election. They will compare. Okay, tell me give me your MAC address. Our priority number is the same thing. Our system ID, extended system ID is the same thing. So the only thing that we can use now is to use MAC address. They will now use MAC address to make that decision. That is key. So now you know how we choose who becomes the root bridge. We use beads. And in that bead, the most important thing we use there is the MAC address. Don't ever forget that. So don't go and crown any switch with the lowest MAC address win the election. Say any switch with the lowest bid wins the election. Because I can, as we proceed in this class, I'm going to go and tamper with the priority. If I'm able to reduce the priority of one of the switches, that switch is going to win the election regardless of what you have as MAC address. Because priority take precedence over the MAC address. I need to move. Time is going. I'm not giving you guys break this evening because we wasted almost 30 minutes gisting. So take note of that. That is how these things are selected. I want to cover the theoretical part before I go to some demonstration again. So I've shown you guys this. So they just give you an example here. I've explained my own way how they elect the root bridge. They go for anybody with the lowest MAC address. But if we're able to reduce MAC address in call, that is going to take precedence. In fact, let's do that with our switch. Let's reduce MAC address of that switch A that lost that election. So now we want to read this election, guys. Now command. We know that this guy didn't win the election. So he's telling us about the rules. Say, I'm not the president too. This is the president. You know, we say, okay, you know what? We can help you out now. I want to read this election now. What I'm going to do that. Spanning tree. I'm looking for the command. Mode. VLAN 1, I believe. No. Spanning tree mode. No. Okay, I think it's spanning tree. So you guys, you think I have all the commands in my head. Sometimes I forget these commands too. Okay, go see the command here. That's why you need to know how to use question mark. Spanning tree, VLAN 1, priority. I want to change the priority, but I need to bring something to your notice. The priority can be in the increment of 4096, meaning I can start with 0. I can then follow by 4096, add another 4096. That is how you'll be going. So if I like now, I can reduce the priority of this to 4096. Spanning tree, VLAN 1, priority 4096. And guys, if I do this, you will know that this priority will be lower than the other one. So you see that this guy is going to win the election. They will scatter everything and say, no. You can't be the president. They thought he'd be. This guy is better than you. He has a lower priority. And the guy will say, but me, I have a lower marker. This is not here. We've shifted the goalpost now. The rule of the game is priority comes before MAC address. You find out now. So let's see, show spanning tree. Let's see. Guys, I am now the president. Switch A is now the president. What happened? We change the priority number. Didn't see thumbs up there. If you guys are flowing with me, can I get your thumbs up? I changed the priority number. So you can influence the election. Sometimes there's a need to do that. Thank you guys. Why? You just bought a powerful switch on your network, robust switch. And that's what you want to use. You want the guy to be the president of your network. You cannot allow regular election. Regular election will go and give the election to one of the old dead switch in the organization. And all the way list, and that will going to perform. It will going to affect the performance of your network as well. And this is the painful thing about some big organization. They don't factor this in. They just drop switches. Lead switches will just litter everywhere. Then when one of the old switches can't go win the election, all the way leads to that guy. So all the decisions that other switches will be making on the network is the reference to that old school switch. You cannot allow that to happen. So how did we rig this election? You can't change MAC address, but you can change priority number. So let me remove that command and show you another command. So if I'm here, let me quickly finish everything. I want to remove that command so that we can go back to the way we were before. So I've removed it now. This guy is going to lose that election because based on MAC address now, the other guy is going to be better than this. So let me remove that. Okay, I've removed that. Let's see. Okay, now we're back to where we used to be. So they're telling me now that the root bridge is the other guy. But there's another way to also do this. Let me just show you the second command. And that one also will reduce the priority. Watch out. Watch out. Spanning tree. Instead of saying spanning tree VLAN 1 priority, I can just say spanning tree root primary, because I can have two different primary this thing. So if I have decided to say this guy is going to build the roots and is the primary root bridge, do you know what this switch is going to do? It's just going to reduce his priority as well. If I go down here now and see so spanning tree, you see what the guy did? He just reduced his priority so that it can be lower than the other guy. And as a result of that, it won the election. So I can make a bold declaration and just say, you are the root bridge by that command. Now, and you now know how to go and change your priority number. Or I myself change your priority number. Either way, we make you the king of the network. This is how we influence this election. So take note of that, guys. I'm going to have to run now. Show you two major commands. So they elect the root bridge. And of course, if you don't want to leave it to chance, you get involved. You change the priority number. Or you tell whoever is going to become the root bridge to become the root bridge. But if you don't get involved, everything go on normally, you may likely get a switch that is not supposed to be the root bridge to be the root bridge. Now I want to talk about the cost. I said something earlier. The switches will determine the best path to reach root bridge. So let's say this is our route now, for instance. This is, let's say switch A, switch B. Let's say switch A want to make decision on how to go to this root bridge. How will it decide? How will you know the fastest link? There is a table for us. Any link of 10 gig has a cost of 2 under spanning tree. There's another one called rapid spanning tree. We're coming to that later, which is 2000. But let's stay with spanning tree first. If your link cumulatively is 1 gig, the cost is 4. If the cumulative speed is 100 Mbps, the cost is 19. If the cumulative speed, is 10 Mbps, the cost is 100. So what I'm trying to say is this: switch A is directly connected to root on this link. Let's say the speed of this link is 100 Mbps. But when it goes through the other parts, one of this link is 1 gig, the other one is 1 gig. Cumulatively, this one will give us 2 gig. So you and I looking at this connection now, you know that the other routes, this fast route will be faster than this direct connection. And what is the cost of this 100 Mbps? Based on this table, is the cost of 19. The cost of the other route, 100 gig, 1 gig is 4. So on this link, the cost is 4. On the other link, the cost is 4. So the cumulative cost to get to that place is 8. So the switch A will now look and say, you know what? I'm not born fool. This right link is faster than the left link. Then it will block this link and decide to be going through the other link. So that is what I was trying to tell you guys, that the cost is based on bandwidth. There is an algorithm in place. So the switch will put the algorithm to work to calculate the cost. So if it has two different links, it will just look for the one that has the lowest cost to the root bridge. The higher the bandwidth, take note, the lower the cost. Look at 10 gig, cost of 2. 10 Mbps, cost of 100. The lower the bandwidth, the higher the cost. So higher cost is not good. In fact, let me tell you something, guys. Everything about switch is low. Low is better. Lower MAC address, lowest cost. But the speed must be high. That is how the switch make their decision. So when I say they will use speed, actually what they put in the table is cost, and I'm going to show you. And that cost is based on bandwidth. And we can also lie to the switch and change the cost. If I want this switch now to go through this thing directly, I can lie to this switch now and say, so you think you were wise, but can a man die, can a man bury him? This place is cost of 8. I can lie to the switch and say, you know what? This direct connection is a cost of 7 by configuration. But we don't need to do that. That is if you want the switch to now. So the point I'm making is when you're talking about spanning tree, at the advanced level, you can manipulate spanning tree. At this low level, you should be able to manipulate based on the ones I'm teaching you guys now. But there are some I will not talk about in this class because they are beyond the scope of TCL. So take note of that. So that's how one of the things I need to talk about. So I've talked about root ports, I've talked about the destination port, I've talked about alternate ports. So we're not going to waste time on all of these ones. This is going to be the last part, and then I will give room for question. Sometimes you have multiple equal cost paths. You follow the right, the same cost. You follow the left, the same cost. What will the switch now do? When we have situations like that, we need to know how the switch will make that decision. Let's find out. When a switch has multiple equal cost path to the root bridge, the switch will determine a port using the following criteria. So the switch want to know, now that I have a tie with the cost, what will I do? It will have to now find out the lowest standard bid. I'm coming there. If that one there's a cost, there's a tie already, it will use the lowest sender port priority. If there is a tile again, it will now use the lowest sender port height. Let's see. They gave us good example here. Let's see. Look at what we have here. There are 4 switches on this network, and this guy won the election. The guy won the election. So there's a problem. If switch 2 want to go to the root bridge, if he follow right, the cost is the same. If he follow left, the cost is the same. What I mean by cost, the speed is the same at both ends. So how will this switch 2 break the tie? It still boils down to that bid now. It will now look at the 2 switches on the path to that destination. I have switch 3 on the path to my destination. I have switch 4 before I get to my destination. Between these switches, 2 switches, who has the lowest bid? And you guys know what makes up the bid now. Anybody with the lowest MAC address will have the lowest bid. So the switch will now decide to go through the person that has the lowest bid and block the other side. That is when it's considering the lowest sender bid. If I pass through this guy, what is the guy's bid? If I pass through this guy, what is this guy's bid? When you have a tie in this kind of scenario, this is how the switch will break the tie. That is one scenario. We have another scenario. What if you are connected to just one switch? Between these switches, this guy won the election. This guy has 2 different connections to the switch. So meaning, and the cost is the same. We can't use cost. The bid is the same because we are just on one switch. So we cannot use lowest sender bid. The switch will now descend to another thing called lowest sender port priority. What does that mean? Every port on the switch have what is called a port priority. And you know the funniest thing? The port priority is the same again on this port. All the ports on the switch, their port priority is 1 to 8. We can change this. We can fool the switch to change the port priority. So there's a tie. So look at what we have, the problems we have. In terms of cost, there's a tie. In terms of bid, there's a tie. In terms of port priority, there's a tie. So how will the switch break this tie? It needs to break this tie. That is the way. We need to find a way to break the tie. That's when the switch will now go to the last part here. And look at what it's going to do. The lowest sender port ID. Port ID is different from port priority. Port ID is different from port priority. So look at what the switches do. So this switch here, it needs to block one of the links on its own side, but he doesn't know which one to block. So if he's considering port ID, there are 2 ports on the root bridge. One is port /0/1. The other one is port /0/2. And we have said in this class, when you are talking about switch, the lower is better. That means F0/1 must not be blocked. When you are talking about port ID, is of more value when you compare it to F0/2. So between these ports now, port 2 is the one that we can block. But you cannot block any port on the root bridge, guys. So this switch 4 will now say, you know what? Or let me say Spanish tree will say, you know what? Since I cannot block any port on the root port, I'm going to go to on the other side and block port 5. How did he make that decision? We want to use port 1. Why did you decide to use port 1? Because lower is better. You're talking about switch. Port 1 is of more value. So this other link is open. So when there are scenarios like that, the switch will always find something to break the tie if you don't get involved. Because if I get involved in this now, I can manipulate any of these decisions. I can tell the switch, I can fool the switch to say, you know what, this port ID, this side is better. It's a lie, this one is not good. Then this other port will be open. So these are different scenarios you have when you have more than one switch on your network. So these are things you need to know. I'm going to stone land this plane. Let's quickly move. So the switches have what is called hello timer. That's the time they send the VPDU between themselves. They have what they call forward delay timer. That is the time they use to move from forward from I'm rushing now. Listening, sorry, yes, listening to learning to listening, learning, yes, and forwarding. So what do we mean by that? You hear or say something like, okay, let me give you a scenario. Anytime you plug computer on the switch, you see that it takes a long time for the port to start dishing out information or for you to even get an IP address. And the reason is because that port is going through what we call different port states. So your port on the switch at the initial stage is in a block state. If you are not plugged any cable, say it's in a block state. Then when you plug cable, it moves from that block state to listening, from that listening to learning, and from learning to forwarding. And this process of moving from block state to listening to learning and forwarding takes 50 seconds. And so there is a delay in between, or let's say a timer in between. So the forward delay timer is what we are talking about. And of course, the max A timer is a time of it takes this topology to change. When I say to change, you plug another switch on the network. They have to understand that there's a need, and it's a new person here. We need to be able to talk to the person. So all of these timers are changeable, but we don't advise you change. So the switch will be talking within themselves. They have a LO timer. That is like to keep track of their neighbor. Forward delay timer is when the ports move from one state to another. Maximum age timer is when it takes the topologies to converge when there's a new thing. That's not where I'm going. I'm going somewhere. This is what I just explained to you. So for the switch to move from blocking to listening, it takes 15 seconds. Listening to learning, another 15 seconds. Learning to forwarding is 20 seconds. So we always say for a switch network to converge under spanning tree, it takes 50 seconds. But this is no longer acceptable in the world of truth. That's another problem with people out there. We want to migrate to rapid spanning tree. There is a new technology, advanced spanning tree, that is out there. And you're going to see it at work. Let me just finish this and I'll demonstrate that. So in blocking state, BPDU that we talked about can only be received. MAC addresses, the switch cannot learn MAC address and it can't forward data. In listening state, BPDU can be, sorry, here it can be received only. Here it can receive and send BPDU, meaning the switches can send BPDU to themselves, or that port can send BPDU. In learning state, we can receive and send BPDU, and this is our concern here. That is when the switch begins to now harvest MAC addresses and build the MAC address table. But guess what? It still cannot send data. But this is when the switch can now begin to send data. When that port transition to forwarding state, the switch can receive and forward data. It can update the table, the MAC address table, and forward data. But if we disable the port, nothing happens there. Let me show you all these states on the switch before we finish. Let me show you this. I'm going to plug a computer on that port on one of the switches and show you something. So let me quickly go to that switch and show you something. Show spanning tree. You see now that port is in a listening state that I just plugged now. Now if I put enter again, the port has moved to listening states. That port is moving gradually. If I go again, you see the port has moved to learning states. If I go again, you see that the port has moved into forwarding. Let me see. You're going to see that port. Okay, yeah, it's going to move into forwarding. You watch out now. That port has moved into forwarding states. So let me do it again. I can shut down that port and bring it back again. That's port 1. So that you can see this thing at work. Interface F0/1. Shut. So let's put do show spanning tree. Spanning tree. So the port is gone now, guys. So let's now bring it back. No shutdown. No shutdown. And quickly issue that command. Do show spanning tree. The port is coming up. It's in a listening state now. LSN. If I put that command again, you see that the port will move to learning states. So you see, the port has moved to learning state right now. That port is coming up gradually. And then finally, that port will move to forwarding state. This is what we call, what is it called? Port states on the switch. So the moment you plug your to a switch, you realize that that switch, that port on the switch you plug to, we move through all these stages. But in a world of today, this is no longer acceptable to us. Let me show you why. Let's go through something here and then we'll see. The last slide here now, for now. The last slide here. Okay. Let me talk about a few things here. So this spanning tree we've been dealing with all this while, guys, is called a VLAN rapid spanning tree. Plenty story. What do you mean by a VLAN spanning tree? This is a spanning tree that can create different instances for different VLANs. And as a result of this, we can achieve redundancy. But that is beyond the scope of this class. I won't say more than that. Now, this particular technology we're talking about belongs to Cisco. VLAN rapid spanning tree. So what do you mean by that? Let me show you the variations or evolution of spanning tree. There are different spanning trees out there. Look at different spanning tree. The regular one that people know generally is spanning tree. It belongs to the open source. When I say open source, any vendor out there run it on their equipment. But Cisco came out with the one they call VLAN spanning tree plus. They worked on this to get this. And this you can only see on Cisco route, on Cisco's switches. So in a sense, the one we are running right now, because this one was so confusing to me as a student as well, the one we are running on right now is a VLAN spanning tree plus. It means it can create different spanning tree for different VLAN, different instances rather for different VLAN. But you know what? Cisco left this and moved to rapid VLAN spanning tree plus. The open source people also moved to rapid spanning tree. So you can only use this on Cisco route, on Cisco switches. There are others I'm not going to talk about. So what is the difference between this rapid VLAN and this regular spanning tree? You watch it for yourself. Let's go back to this switch we had here and connect two links again, like we had before. You will see something now at work. Thank you, guys. Earlier, when I removed one of the cables, you saw that it took almost forever before the backup came up. Now we are going to move these switches to rapid spanning tree, not the regular rapid VLAN spanning tree or the regular spanning tree of Cisco. We are going to move these switches to the latest technology that is faster than the old one. So now this guy has blocked one of the links. It has opened one. So before we yank off the link that is active, let's go to the switches rather, and move them to rapid spanning tree. Watch out. Spanning tree. What is that command? Mode. See what we have here. See the two options we have. I can say spanning tree mode per VLAN spanning tree, which is what we are currently running. But this is what I want, guys. Rapid VLAN spanning tree. So I'm going to do that on this switch. I'm going to go to the other switch and do the same thing. Rapid spanning tree. So watch out. What's going to happen? I'm going to do that here. So I've moved the two switches to rapid spanning tree. Now shows see something. Shows spanning tree. Look at what it's going to show you. Cisco, instead of them to call this one rapid spanning tree, they still told us rapid pavilion rather. They still use the name of the open source, which is rapid spanning tree protocol. That's their own, how do you call it? That's their own discretion. It's not a problem. We have moved. But you guys watch something now. I need your attention now. That link that is active now, I want to get rid of it. Boom. What did you see? The backup just came up. We didn't even waste time. And you now tell me, somebody will have 10 switches on his network, 15 switches, 20 switches, and you have decided to activate rapid spanning tree, or let me say backup link, and you don't even know that you should move those switches to rapid. So when one link goes down, it takes almost forever, even though it's just 50 seconds. But that 50 seconds is a lot in the world of today, in our world today. It takes almost forever before the backup list will come up. If I bring that thing back, watch out. I think I have undo here. Undo. You will see how long it will take. That backup, backup link. One of the link will be shut down quickly, and one will come up. Ideally, is the one that will remove there that should come up. Let me watch this. This doesn't make sense to me. I need to find out why that one's happening. So let me yank up this again. Boom. See, the backup came up automatically. What about the port on the switch where we connected the computer to? Let me shut that port down again, and you see how long it takes that port to come up. Same port we were in before. That interface, shut it down. Shut it down. And now, let's say show spanning tree. This shows spanning tree. You can see that that port is gone. So let me bring it up again. No shutdown. And this shows spanning tree again. The ports, where is the port? Port is down. Why is it going? Okay. Fair catch me. So the thing has moved into from blocking into forwarding. It did not even move into listening. It did not move into learning. It just jumped straight to forwarding. So when you go to this advanced one, your link is faster than the regular spanning tree. That is the point I'm trying to make there. I'm going to now give room for questions, guys. Please feel free, express yourself and ask questions.